sorry. No, that's what I'm saying. No, that's good to know. But it was really nice to know what's being. Okay.
It's a good way to meet different.
Yeah.
That makes your education.
Okay, because you can run it. Oh, okay. So, yeah. No, it's good to know. So, it's really good to know.
I don't know, maybe I'm taking all the same classes.
Sorry, that's the second time. Ready? Yes. Okay. So today we're going to do income. So he asked me to teach the lesson. We're actually taking a break from the recursive neural networks, and so he will be finishing the lesson that we said we did last time. Okay. Today, I will be talking about generative models. Okay. Maybe some of you already saw them, but I will give an introduction, some examples of how certain things were done before deep learning, and then I'll move on to the deep learning phase, which is the one we're interested in, right? If we finish earlier, ask questions or go home. Okay? Okay. So, let's start with the concept of unsupervised learning. Okay? Is any of you able to define what unsupervised learning is? Yes.
It's when we basically have unlabeled data and we're able to learn something about the data through, statistics on that data or something like that.
Okay. Yes. Precisely. So, first of all, in unsupervised learning, the data is provided with no labels. So, actually, tests like classification or like even regression are pretty much impossible. But there is still something that can be learned from unsupervised data, right? So, which purpose do we have for unsupervised data? As Matt was saying, we can still learn something about the distribution of the data, some intrinsic characteristics of the data itself. Okay? Or themselves. Is it plural or is it not data? Technically should, right?
Data is plural in something.
Right? Yeah. Because the singular is datum. Right.
Yeah.
Thanks. Okay. So, do you all know what a manifold is, except for the ones that already have a PhD in math? Does any of you know what a manifold is? It's a bad concept, so even the ones that know don't want to say it, right? Yes. Okay. Okay. A manifold is a structure that is in some Euclidean space. Okay, like in this case we have R3, right? The three-dimensional Euclidean space. We have another, like a subspace of this that has a different shape. Okay, there are a lot of mathematical axioms to define a manifold. Like a manifold should be differentiable at each point, should be C something smooth. But this is not something that you want to know. But Why am I explaining this? I'm explaining this because usually the data that we have, okay, like the data that we have, we can always define it as like each data point that we have, we can define it as a point in an n-dimensional Euclidean space. Does it make sense? A yes? A no? Yes. Okay. So when we have one data point, we define it basically in the Euclidean space where it belongs, right? But if we have a lot of data points, we can actually try to define the manifold on which they lie, right? Like in this case, for example, we have torus, you call it in English. We have a donut, and the surface of the donut is a manifold, okay? And we can actually, like, if we lie on this manifold, we can move anywhere on this manifold, but if our world is the manifold, we cannot move outside of the manifold, correct? Does it make sense? It's like we live on the world, which is like the surface of our world, right? It's a sphere. That's not true, but it's a sphere, right? And we can move on the surface, but we cannot move up and down. Don't play the smart with me saying that we can fly or something, okay? If we walk, we can't. So we can consider that as a manifold. The same thing happens with our data. Usually our data comes from a manifold in an n-dimensional Euclidean space. So if we can learn the manifold, right, we can actually, for example, generate new data points that actually didn't come from the real world, but are plausible data points, right? Because let's say I have a point here and a point here, okay? But this is the manifold of my real data, everything that could come from this distribution, okay? So if I have these 2 points and I am able to understand the shape of the manifold, I can move from here to here and find all these infinite points in between, the ones that I really have. Does it make sense? Like, does everybody follow? Okay. So this is, for example, what we want to do with unlabeled data, which actually it is a thing that in the medical field now they're doing a lot, in computer vision they're doing a lot, I think in natural language processing too, but I am in image analysis, so I know nothing about that. And so, another thing that we can learn from unlabeled data is, for example, the probability distribution of the data itself. I could be able, for example, to infer the probability density function of an n-dimensional data, right? In this example, for example, we have different data points all lined here, right? And the guy that did this was able to infer for the probability density function for the x-axis and the probability density function for the y component, correct? So once I have those two, maybe I will be able to see the probability density function on the data itself. Like, for example, in this case, if x and y are independent random variables, for example, just multiplying the two probability density functions, I will be able to find the probability density function of the joint probability distribution, right? Does it make sense? Yes. Perfect. Of course, if we know that they are not independent, then it becomes a little trickier, right? So. These are two examples of things that we can do, that we can try to learn from unlabeled data, right? And as you know, in the world we have a lot more unlabeled data than labeled data. So if we can actually leverage some knowledge from there, we can maybe also make it easier for our algorithms to learn something from the labeled data too, right? It can make our classification even better, correct? Good. So, as I was telling you earlier, like we will review a couple of old school methods that were used. Probably the mathematicians will know them. For the others, don't be scared if you don't understand, but ask, okay? Because like, especially the first one, I saw it the first time 2 years ago, and I understood it 6 months ago. So, please ask. It's not that difficult, it's just that you need someone that can answer some questions, okay? So the first one I wanted to talk about is principal component analysis. Has any of you ever worked with this, know what this is? You know everything, right? Okay. You do? Okay. Okay. So this is this was one of the first methods that actually like I was taught for shape analysis. Doesn't matter if you don't know what that is. But for example, okay. So let's say that we have a lot of data, okay, in n dimensions, right? This data, as I was telling you, rely on a manifold, and I want to try and learn this manifold so that I will be able to like move back and forth on this manifold and find new examples, right? So, okay, for this method, the first thing we do is basically putting the data all in one long matrix and find the eigendecomposition, okay? So we find a square matrix that is diagonal, right, containing the all the eigenvalues of the matrix, and we will also have another matrix that contains the eigenvectors, okay? I hope all of you remember from linear algebra what eigenvalues and eigenvectors are, right? Yes. No. You don't remember? Guys, someone can say no and there's no shame in that. I want you all to know this. Okay. When we have a matrix, the eigenvectors are those vectors that multiplied by that matrix, okay, give the vector itself multiplied by a constant. Does it make sense? Yes?
Yeah.
Okay. Okay. So, so there's a bunch of them for this kind of matrices, okay? But when we find them, okay, we can define a change of basis, right? Like if I have my my y and x axis, right? A change of basis would be something that just rotates them. Simply that, okay? Soon I will tell you why we do this, because explained like this seems like a stupid thing, okay? So, the first thing we do is finding the eigendecomposition. So, eigenvectors and eigenvalues of the matrix. So, we only want to keep the largest eigenvectors. That means the eigenvectors that have basically associated to the largest eigenvalue. Okay? This is basically to say that there are some dimensions in the data that don't count. Some dimensions for which the data doesn't change enough for us to be interested in it. Does it make sense? I have a picture later, and that maybe will make things a little easier. But like, are you all following me?
Yeah.
Okay. Thank you. I need validation. So then, once we have found this, we can project each new data we have onto this change of basis that we found, which is actually also a dimensionality reduction, right? Because as I said, we got rid of the eigenvectors for which the eigenvalue is so small, that means that for that dimension we don't care, right? So we have this method that can help us to basically get rid of these dimensions that we don't care about, and so having to work in a space that is smaller usually brings better results, because a simpler space means that I have to take care, for example, of less features, and so for example, my algorithm in general doesn't have to decide if certain things are actually important or not. We can just say, no, these are already just small. So only take care of the things that you really need, okay? So, okay, this is the picture. In this picture, we have a plane, okay? A plane is a manifold. This is a 2D plane in a 3D space, okay? So we consider this plane a manifold embedded in the 3D space, okay? All our data actually lies, not all our data, but like a lot of our data lies on this manifold, and some of our data lies a little bit up or a little bit down. Can you see it? Does it make sense? Okay. Now we can have a change of basis when we apply PCA. The first step, remember, is to use the eigendecomposition, and then we get rid of the dimensions that we don't need. So since we are in a 3D space, we basically are able to rotate the axis in these two directions, and of course these eigenvectors will always be orthogonal, right? So that they always have a 90-degree angle between them, and so we are basically in the same position from where we were at the beginning, right? So we're basically rotating it so to align the axis towards the dimension of the biggest eigenvalue, yes, but like the eigenvalues, they also represent the biggest variance in the data. Does it make sense? Like if I move along this axis, for example, I find a lot of data and a lot of variance between here and here. But if I move on this, I find less variance. Can you see why? Does it make sense what I'm saying? Okay. So I apply PCA, and I basically get rid of the third axis, because as I was telling you, like in this direction and in that direction, I don't have a lot of variance, so I don't care about that. I decide that I can cut it off without having actually a loss in the representation. And as you can see, I brought the representation from a 3D to a 2D space, which is a simpler one, and I can work in this one. Does it make sense? Yes.
How did you find this plane?
How do I find this plane?
How did you find, like, how do you know this 2D plane? Like, I understand you have all these data points.
Mm-hmm.
Where did the plane came from? Did you figure out the plane, or?
No, because you have that is the thing. You have the data points, right? And you're inferring where, like, the manifold from the data points using PCA. Does it make sense? Like, basically what happens is this is the plane that you find when you find the eigendecomposition. Okay? That 2D is the one that you obtain when you get rid of the third dimension, right? You don't have to define it as a function of like f of x and y equal some nice and dandy formula. Like you just infer it from the data. Does it make sense? Does it answer your question?
Yeah.
Okay.
You want to like Google a singular value decomposition or something like that, right?
Yes, you use a singular value decomposition. Yeah. But yeah, I mean, I don't go into a lot of details on how you do it because like I will just confuse you more. If you can understand what this does and roughly how it does, you should be good.
Comment for this one. Singular value decomposition for any given matrix, it doesn't have to be square. Which is the eigenvalue decomposition should have to be a square matrix. They're
Yes.
quite different things. The eigenvalues are square root of, or I get square root of the single brackets. And here, I think, as I understand, when you get rid of the eigenvectors that's associated with the small eigenvalues, you get rid of all these outliers. So you keep highly correlated with data.
Exactly.
Yeah.
Precisely. Thank you.
Sorry.
Oh, I was just gonna say, so is, like, I'm trying to visualize it, but that plane, is that like minimizing the projection of, the minimum projection of all those,
Basically, yes. Basically,
to
yes.
reduce that
Yes.
dimension,
Yes.
and it minimizes that
Mhm.
of all, okay. And then how do you know, like, how many dimensions you want to reduce it?
Well, usually you are the ones that decides. Like a lot of them end up to be like a lot of them from the things I worked on, like ended up to be zeros or very very close to zero, so you can just delete them. But yeah, it's a thing actually you got to decide. Like knowing your data and knowing what your purpose is. But, yeah. Yes. I mean, in this class, I doubt that Bergen will want you to do anything like this. But to be fair, there's plenty of packages that do this. So yes.
So if you want to measure of the variance that you keep after the projection, the sum of the eigenvalues that you keep over the sum of the total eigenvalues there initially were gives like the ratio of the variance that's retained after the dimensionality reduction. So that can tell you kind of how many dimensions you may want to keep.
That's okay. That's fair. I never used that trick. Though. Did you understand what he said?
Yeah,
Okay. So yeah, actually, yeah, it's a fine trick. Thanks. Thank you. Any other question about PCA? Okay. So yes, as I was saying, we obtain a simpler and a better description of our data, and the dimensionality reduction is achieved. Does any of you see what the problem is in PCA? It is a super cool method, but it has one pretty big downside. This is kernel density, but it doesn't matter. It's linear. Like all the variances that you find, all the things that you can do with PCA are linear. So if you have data that is highly nonlinear and like PCA can become really, really bad. Does it make sense? Okay. That is the downside of PCA. Now, let's talk about another thing that can be done with data. This is actually way easier than PCA. Like no singular value decomposition, no fancy stuff. In this case, what we want is to infer the probability density function from which our data was generated, right? But we only have samples from this, and we don't have the whole data nor the density itself. So this is a simple method that treats each data point in the training set, right? In this case, I put a Gaussian distribution, but you can put a lot of like the distributions that you like, pretty much. But let's talk about like the Gaussian kernels. Each of our data points, in this case, we call them xi, right? So for each of them, we construct a Gaussian distribution with a fixed standard deviation for all of them, and our mean will be our xi. Okay, so if we have n data points, we have n Gaussian distributions, and in each distribution, the mean is one of our data points. Okay, simple as that. Then every time we obtain a new data point, for which we want to know the probability that this data point could be generated, right? We simply use this function, which is the sum of all the Gaussian distributions, right, that we found, evaluated at our new point x. Okay? So, and then we normalize. Okay? This is like a simple normalization factor, which is n times the standard deviation for the variable. The standard deviation. Does it make sense? This maybe makes more sense. Okay. So in this example, we have 1, 2, 3, 4, 5, 6 examples in our training data. Okay. So for each of them, we constructed these Gaussian distributions, right? So now, if I obtain a point, I don't know, like a point here, what I do is evaluating this point for this distribution plus the same point evaluated at this distribution and so on up to our 6. Okay? Then we normalize and we will have the probability of our point, our new point, to be part of this distribution. Okay? So, and as you can see, the blue line is actually the probability density function that we were able to construct through kernel density estimation in this case. Does it make sense?
Yes.
Any questions? Okay. I mean, this is way easier than the previous one, isn't it? This is very, very computationally simple. So these are some of the things that we can do with our unlabeled data. These are two of the many old school methods that we have. But can we do something with deep learning? Of course we can, otherwise we wouldn't be talking about this, right? So, okay. There are different methods and architectures that are studied today, in the sense that, like, some of them, the ones that I will talk about today, have been designed less than 5 years ago, and people are still studying them and trying to understand them, even mathematically. But okay, the ones that I've seen more used for these purposes are two, and we will talk first about variational autoencoders. This is a paper that was published at the ICLR 4 years ago. If you have time, I would advise you to read it. It's very interesting. So let's start with it. Okay, do you know what an autoencoder is? An autoencoder is a neural network that is trained to get an input, and in the end reconstruct the input, basically. Okay? So the input and output, I want them to be the same thing. Okay? This sounds like a stupid idea, but it's not, because we have an encoder and then we have a decoder. Okay? The encoder, for example, in the space of images, what the encoder does is actually mapping every image, so every data point, from the image space to a smaller space. Okay? As I was telling you before, a smaller space is easier to handle for us, but especially for the algorithm, right? Because in a smaller space, it can only keep the information and the features that it really needs for the task at hand. Does it make sense? Yes?
Yep.
Yes, thanks. So, we need obviously to have input and output to be the same, right? Because the decoder has to reconstruct the original image starting from the hidden space that we find here, right? When, we call it hidden space, latent space, as you want to call it. It's simply the space of the dimensionality reduction that we obtain, okay? Like I can map this very friendly cat to that is, let's say, a 28 by 28 image, so like 784, I think, something like that, pixels, to a vector that can be 100, for example. So I have a dimensionality reduction that of almost like 12, like 80%, 85%. But I also have to demonstrate and force the system, the algorithm, to be able to reconstruct it to show that this space is sufficient to retain the necessary data and the most important data that this cat gives me. Does it make sense? So this is what an autoencoder is. Okay. Now, a variational autoencoder is an autoencoder, but uses a couple of tricks. To actually learn the manifold in the low-dimensional space of the data and be able to actually generate, in this case, new friendly cats that don't come from real world photographs, but that look real, right? So, the first thing that we do to train is to encode the input to a lower dimensional space, as I was telling you, right? So we go through the encoder. This is the first part. In this case, for example, they use convolutional layers, but the first ones weren't using really convolutions. They were using just fully connected layers, these kind of things. Then, okay, we want to force the space, our latent space, we want it to be basically a representation of a unit Gaussian distribution, so mean and standard deviations, okay? So we minimize do you know what the KL divergence is? Have you ever heard of it? The KL divergence is, no, thanks for that. Okay, I don't have a formula here, but basically the KL divergence is a way to compare how close to full probability distributions and density functions basically are, okay? So it's basically the integral over all x of P of x times the logarithm of P of x over Q of x, where P and Q are two probability distributions, both on the random variable x. Okay? So, of course, like, since you have the logarithm of one over another thing, one thing over another thing, if the two distributions are equal, you obtain the logarithm of 1, which is 0, and so the distance between the two distributions is 0, right? But if they differ, right, this is not 0 anymore. This increases, right? So I want to minimize this so that basically in my here in my latent space I obtain a vector of means and a vector of standard deviations, right? That come from the unit Gaussian distribution. So I basically force it to become a specific distribution. Okay? So, questions? Did you understand what I just said?
Can you repeat again?
See? Okay. Yes. So, what I want is to force the latent space, right, to be simply a vector of means and standard deviations. Okay? And I actually force it to be means and standard deviations in n dimensions, the number of dimensions I choose, of the unit Gaussian, right? So, okay, yes.
Why are we doing this?
Why are we doing
Why are
this?
we going from the input output of that network to the new
Latent spaces?
yeah. So what's the reasoning behind doing this?
For a dimensionality reduction.
Yeah.
Sorry, maybe I'm not understanding this.
Just taken the encoder output and given it to the decoder and be done with it. Then why are we having a mean difference in relation vector? What is the reasoning behind this?
The reasoning is that I sample from the Gaussian distribution with these means and these standard deviation, right? I will sample a vector that will be fed into the encoder. Okay? So, if I force the whole image space into this, right, I can simply sample a vector, right, and obtain a new image. So this is what I want. That's why I do this. That's why I'm forcing it to be. That's why I'm forcing it to be a distribution that I know how to sample from. Does it make sense? Maybe I didn't understand the question.
I mean, you could have just removed the two extra layers in between and taken an encoder network directly to the decoder network and bypass all that.
Oh,
Yeah.
here? Like removing this and going to...
Yes, you could have just gone straight to that.
Oh, you're asking me why do I find the means and standard deviations if then I sample? Why don't I simply force that to be the sampled vector? Because otherwise I wouldn't be able to... Okay, if I don't do that, forcing the how can I say? Basically, we are actually, in this case, we are actually relying on the fact that when we minimize the KL divergence, it's actually only an approximation, right? So the means and the standard deviations give me, in the end, they will go towards be always like zeros and ones, right? But they're not properly zeros and ones, and so I still retain some of the information that I need. Does it make sense?
Yeah.
So it's a little bit difficult to explain.
Very common than ask at the same time.
Yes.
Actually, mean and standard deviation is sufficient statistics. That means it will give you a lot of information about the whole thing.
Exactly.
But the matrix is sparse. If you just do it on a sample predicted vector, you won't get all the information. But when you get the information from mean and standard deviation, it will get a lot. Okay.
Yes. That is what I was trying to explain. Yes. Thanks. Do you want to ask?
Well, is that correct, actually?
Yes.
Okay.
That was what I was trying to explain. Yes.
So a couple of questions as well. So the decoder network, what are we actually learning? Because the label is not really provided. So
In the decoder? Oh, we are. Yes, I'll explain it. Well, I can explain it. I am basically just using the Euclidean distance on this. Because like this and that. At the beginning I put an input in, right? But garbage comes out.
yeah.
But I wanted to force it to be the same, like, so actually my label will be my input on this.
Okay.
Does it make sense?
Okay, and okay, I think so. I'll ask my second question, but I think you've already kind of covered it. But I'll say it again. So all the mean vector, all the elements in the mean vector won't have the same weightage, and I'm guessing that the decoder network already kind of that the network kind of automatically weights each mean vector upon. It automatically weights the mean vector depending upon how it can reconstruct the image, right? Is that
How can
correct?
we what?
So the point of the decoder network is to weight the mean vector in some
No, because I'm sampling from that standard, from that Gaussian distribution.
So my point was that maybe you have the entire mean vector, right? But not all the variables are equally important, right? So how do you why in the entire algorithm do you account for that?
Well, the means are different in each row. They're
Yes.
not equally important.
Okay,
I mean, when I obtain a mean vector, like the whole vector will have different numbers. It's not like, so that already means that some are more important than others, that some, like, is this what you were asking?
and that's fine.
So the mean, that's basically the length of n dimensions that you choose, is that right? The mean vector. So the number of means you have are basically like a
Yes,
parameters you choose. And so is it that the mean vector is like dimension, it's like that has like the mean of dimension 1 and the mean
Yes.
of dimension 2. Okay. Great.
Exactly. And same thing, the standard deviation.
And so is the sampled latent vector the same dimension as the mean vector and the standard deviation?
Yes.
Okay.
Yes. Is it clear now? Are we understanding? Yes?
Yeah.
Okay. Perfect. Thanks. So then, after sampling, as I was saying, then we give this sample vector to the decoder, so that we can reconstruct the input, right? 1, 2, and 3. So yeah, when we want to generate a new data point, right? After training, we want to generate a new data point. We generate two vectors of means and standard deviations, and then we sample, and we put this sample into the decoder, okay? And in this way, we are able to generate new samples from the same distribution of the real data that we have. Some examples are these. I don't know if you ever saw them. I mean, I also put the link to the place where you can find it. Do you notice anything in these pictures? I mean, they look fairly real, don't they? But are they actually like very high quality? Not really, right? And here, like, you have seen MNIST to like be nauseated about it, but I put this image mainly because I wanted to show this. This image shows the continuity of the manifold where the data lives, right? Because as you can see, what they did here was actually generated this, well, actually 1, 2, 3, and 4, but let's say this, okay? So, means and standard deviation to sample this example, right? And then they generated this example here, and like the means and standard deviations of these. And so they changed that vector like in steps. And so you can see that actually the whole manifold of the data is continuous, because at each point that I can choose between the 9 and the 6, right, there are infinite many data points that I can generate now that I have learned the manifold of the data. Does it make sense? Yes? Okay. Okay, so the generation is actually fairly good, and we have a dimensionality reduction in our latent space, which simplifies everything. For images, and I'm talking about images because I know better about that. Variational autoencoders are actually known to be fairly blurry. This is due to the fact that this is due to a combination of a couple of things. The first is that we are actually using the transpose convolution. Remember the concept of the transpose convolution, right? And that can already like give this a little bit, but usually it does fairly well. It doesn't blur it that much. But in combination with the fact that we are actually training the network to like on the Euclidean distance between the input and the output, right? This brings this blurry effect, because we are minimizing an expectation, and so we are basically also getting rid of the noise, right? Getting like even if you train a straight autoencoder that just goes to the latent space and goes back to the image space, it always have a denoising effect. Okay, so when I keep denoising it, it's like keeping filtering an image over and over again. If you try to do it in Photoshop, like after like 3, 4, 5 times, like you can just throw away the computer and go for a walk. Okay? So
That's a good question.
no, who? You. Yes.
So here we're calculating mean and standard deviation, which is actually the first moment and second moment. If we have more moments, like third, fourth moment, is it going to decrease the blur outputs and give us more?
I am not an expert in variational autoencoders. Like I've been studying them, but I haven't been using them. But if I was you, I would take a look at the literature and see if they tried something like that. If they didn't, publish it soon.
Sounds great.
So, but I don't know. Like I told you, I am not an expert, so I wouldn't know how to answer that. Actually, if you have that answer, come to me again and give it to me. Okay. Any other question about the variational autoencoder? Yes.
Is an encoder ever used without a decoder strictly for the purpose of dimensionality reduction instead of finding like the parameters of a
That is
distribution
why
to draw
we use autoencoders in general.
Okay.
Like the autoencoder, when you train an autoencoder, that is straight what you want, a dimensionality reduction. Like what I do, for example, sometimes is using an autoencoder. Like I train an autoencoder on my data, and then I basically throw away the decoder, and I keep the encoder because of this dimensionality reduction. I already showed that that dimension is enough for my data, and so I just attach my classifier directly to it, so that I only have to train the classifier, right? And it should give me often, sometimes, better results than not doing it. Okay? Any other questions? Okay. So, the last thing we will be talking about today is generative adversarial networks. Even this is actually fairly new because it was published in 2014 at NIPS, which is like Neural Information something system, which is a pretty good conference. So, okay, this is based on game theory, right? Maybe the mathematicians know this, the ones that studied economics know this. Okay, it is based on this. I am, I want to falsify $100 bills, right? And so I want to get the best at doing it. There is a cop that is paid to catch me, correct? So I do my first $100 bill and I pass it to him. And I pass it to him with a real one. So he has two, one false and one real. He looks at them and he say, this looks like a piece of crap. This you made. Yes. So I take it back and I write another one which is better. And I pass it again with another real $100 bills. And so again he has to catch me, and we keep playing this game until I become so good that I am perfectly able to copy, to forge a perfect $100 bill. Okay? This is a concept which is fairly simple, isn't it? Are we understanding? Okay. These guys work the exact same. Okay? I have real-world images and I have a generator. The generator wants to learn to forge data that is very similar to the real-world data. So I started with a vector of noise, right? And I feed it into the generator. The generator makes a sample, and I take the sample of the generator and the sample from the real data, and I pass it to the discriminator, which is my cop, and it gives me a 0-1 classification. 0 means that the discriminator believes that that sample is fake, and 1 means that the discriminator believes that the sample is real. Okay? Then I calculate the loss, and I backpropagate as usual, right? So, sample vector of noise, I feed in the generator, I obtain a sample. Okay, if you read anything that talks about GANs, they usually use this notation. Okay, so Z is my vector space of noise. Okay, G of Z is the sample that I obtain from the generator, and X is my real data. Okay, so we will just call them like this for a little bit. And so we are at the point where we have this classification, and then we calculate this loss. Okay? Can you see the loss? Can all of you see the loss? Okay. So what I am minimizing? No, wait. So I have an expectation, okay, of the logarithm of d of x is the output of the discriminator, okay? So d of x should be 0 or 1. What is x? I just said it. Is a real data. So the function d discriminator of x should return 1 because it's real, okay? And then I have the logarithm of 1 minus d of g of z. G of z is my generated sample. Z is my noise, right? Z is my noise. G of z is my generated sample. And so d of g of z should be 0 or 1?
0.
0. Perfect. So, okay. So 1 minus, like the logarithm of 1 minus this, okay, plus the logarithm of d of x. I am playing the adversarial game. That's why they're called adversarial, generative adversarial networks, because the discriminator and the generator are playing an adversarial game, right? Where the generator wants to minimize this, right? Of course, the generator, as you can see, has power only on this part, because this part comes from the real data, right? But the discriminator wants to maximize this, right? So if we do it in TensorFlow, of course, if we want to maximize this, we minimize this times -1, right? Okay, so just to give you a little bit more information and to have you understand a little better. So if my discriminator becomes good enough, okay, I will have a logarithm of 1, which is 0. And if my discriminator is good enough, I will have d of g of z, which is 0. So 1 minus this will be the logarithm of 1, which is 0 again. Okay?
If gz is good enough, it has to be 1. G of gz.
Yeah, I said if the discriminator is good enough. If the discriminator is good, it will give me a d of g of z equal to 0. If the discriminator, not the generator, the discriminator is good.
The discriminator is the cop, so the cop
It's the cop.
always
Right? So the cop always catches
Okay.
the, what do you call it, the forger?
That's not good.
Yeah, the criminal money maker. I don't know. Okay? So let's go to the place where the generator is actually very good and the discriminator is good too, right? We still have this part to be the logarithm of 1, which is 0, right? But this part will be if g of z really resembles the data, the real data, the discriminator, even if it's really good, will make mistakes, correct? So this will be 1, and so we will have the logarithm of 1 minus 1, which is 0, and the logarithm of 0 is?
Minus infinity.
Yes. Or, for us that don't study math enough, it's impossible to do. So, in any case, it's that is why we are trying to minimize it through the generator. Because if the generator is very good, that thing goes towards minus infinity, and we are minimizing it as much as we can, right? And the maximum value that this whole thing can get is actually 0. Okay? Are we understanding? Okay. I went through this long explanation just to have you work out a little bit of these small things of math, so to understand what does it mean that they fight one against each other. Okay? Of course, I will. course, I would play this game until convergence, but there was a thing I was about to say and I forgot. That's fine. We'll come back if it has to. Okay? So, okay. Oh, yes, sorry, of course. We're playing this game, and as I was telling you, we're treating this as the loss function of our network, right? So we want to minimize this, and so we leave it as it is for the generator, and we put a minus in front of the whole thing, and we minimize that for the discriminator, okay? We are always back propagating both through the discriminator and the we are back propagating through the discriminator and the generator. You will find out that more often than not, you actually have to cripple the discriminator, because it was demonstrated in a paper that there is always an optimal discriminator for each kind of data you could have, okay? So the discriminator, you have to cripple the discriminator, because the discriminator only has to learn a classification, while the other guy has to learn how to generate data. So it usually takes more time, and to cripple the discriminator, you usually out of n iterations, you train the discriminator once and the generator all the other times. Does it make sense? So that actually, because you don't want the discriminator to actually saturate and say, well, we are done, and no matter what you give me, I will not let you win. And if you never win, you don't have any derivative. And if the generator doesn't get any derivative, we're done, right? They are actually known to be a pain to train. I have worked with this, not with the variational autoencoders. I work with this right now, and actually I'm working with these, and they are pretty tough. So, this image is similar to the one before, but actually, as you can see, the numbers are actually slightly more defined. I mean, we're still talking about a 28 by 28 image, so it's not a big thing. But as you can see, still I have this continuity, which is exactly what I want, because it means that I was able to model the manifold in which the data lies. This is a little bit more interesting, actually. This GAN basically is able to generate landscapes. Like, I give it noise and it generates landscapes. Of course, probably it had to see like thousands of different landscapes, but since these are unlabeled data, how many landscapes are you guys able to find in an hour on Google? Right? You can make your own data set and try this thing. So, again, we have a real generation of, sorry, yes?
So, you gave the example of intrinsic install. If I am trying to put 40 color bill, so possibly generator and the discriminator can learn it, but how, because that bill is always going to remain the same.
The real bill.
Yeah, the real bill will always look the same. So discriminator can always compare against the real bill and answer whether it's correct, that the generated one is correct or not. But if you look at the landscapes, there could be multiple real landscapes.
Yes, there are, okay, but okay, this is the thing. The discriminator learns certain specific features that are part of landscapes, right?
Okay, not specific landscape.
Not one specific landscape. Of like, when you look at two pictures, right? You can tell me, okay, this is a portrait this is a landscape, right? So if I'm asking you to give me 1 for the landscapes and 0 for anything else, if I give you a picture of my face, you can say like, okay, this is not a landscape, right? So the discriminator, as I was telling you, it gets really clever very fast, usually.
Oh, so it's like a classifier.
The discriminator is a classifier. It's just a binary classifier that tells you fake or not.
Oh, okay.
Did I answer the question? Any other question? Yes.
What will happen if you train the GAN with 2 specific types of line phrase and landscape?
So we'll be able to map them. Because in that case, you're talking about, okay, I always say manifold, but actually a lot of times you have to model data that lies on different manifolds, right? So if I give it both, then it will say it's 1 if it's either a face or a landscape, and 0 if it's anything else. Does it make sense?
And then what will be the generated in the landscape is very
That is a good question. I mean, usually, since you always start from a vector of noise, right? So that vector, like the generator learns that the vector of noise means something, okay? So usually it means either one thing or the other, but still, like even only on landscapes, you will find some landscapes that are very like twisted and things that you can tell like this is not a photograph, right? So I suppose that there are certain points. For example, if you train on both portraits and landscapes, there are certain points that will be in the middle, or at least it will be in the middle for the network. Does it make sense? Questions? So with GANs, we can actually obtain high resolution outputs. They can look very, very sharp, like not blurry at all. I've seen at CVPR people doing, I don't know, black magic with GANs, really, and certain things are like, what? So these are very, very cool systems. Even though, like, as every system, they have certain boundaries and limitations that actually people are still studying. So yes, and they are difficult to train. This is what I was telling you. They are difficult to train because you really need to like, if you want a classifier, you can even just make a small mistake, for example, in the parameter tuning, given it like a slightly smaller learning rate that it really needed, or like something like that. If you do this with GANs, you never reach convergence ever. And actually, like sometimes, even if you do it, you don't reach convergence because at a certain point the generator and the discriminator basically start like running in circles. Like I give you this, oh, so I do I take a step back. Okay, so I take a step forward. Oh, I take a step forward too, and then back forth, back forth. Okay, this is a thing that has been observed quite a bit. Yes.
So you would train both the discriminator and the generator at the same time. Why? Is there like a reason for that, or could you train them separately?
That is the thing. How can you train them separate?
Or are they dependent because they're both convergent, so you train them together?
I mean, if you're on the cop, okay, and you only see real $100 bills and nothing else, how can you differentiate from anything else? Like if I give you another $100 bills that you haven't seen yet, how can you differentiate from anything else since you don't have a term of comparison? This is the thing. This is the problem usually with neural networks, even with classification. Like, if I give you a mess and I only give you zeros, you say, oh, okay, these are zeros. I learned what zeros are. Ha ha. Then I give you a 7. Oh, this is a 0. The world is made of zeros. Right? It's the same thing with the discriminator and the generator. Like, they need each other because otherwise they don't have terms of comparisons. Does that make sense? Any other question? Okay. Well, thanks a lot, guys. I think we're done then. Yeah, I'll try to Oh yeah, I'm sure they do. But you can I remember at CW this year there was something